and I will go from current slide. Okay, can everybody see the big white blank screen?
Yes.
Good, excellent. All right, now I told a story of all my sad tales. How are y'all doing? Any issues, any problems? By the way, several of you who may have submitted some work, since have been very limited in what I can get on the system because of the hotspot it being so weak and things. I was not able to print but like one thing last night. None of them was from this class, because, and then if you've done anything through Blackboard, I couldn't even open Blackboard. We tried. I talked with a woman this morning who's in charge. She said it has a big draw. If you're on a hotspot, that's not going to be enough signal for it to do. But now, hopefully, I can get back on Blackboard. I can get back to my email, and I should be able to get back to printing things this evening. I did get everything that I had graded and on Blackboard before it shut down, but I haven't been able to put anything on Blackboard since, and I haven't been able to print anything since. So hopefully I'll get caught up soon. So any issues for y'all, with y'all? None? Okay. One other thing. They have opened student course evaluations for spring term. This will be both for full-term classes like ours and for second mini-term classes. So please get out there. You can find it. Well, if you look for an email that told you that the spring term course evaluations are open, if you go to that email, you will find a link, or they usually put it on there. Click on the link, you're right there. And then you log in, I believe is your, let's see if I can remember what the login is for y'all. I think it's your student ID number. I'm not sure. I believe it is. And then your password is your birth date. So your login, I believe, is your 7-digit student ID number, usually starting with 1, 2 something, maybe 119 something, something along in there. And your password is your birth date. It's an 8-digit number. The first 4 digits are the year of your birth. If it were me, that would be 1951. None of you are that old. Then the year, the month of your birth, for me, that would be 01. That's January. And then the last 2 digits are the date of your birth, and that would be, for me, 07. So if you have a single-digit month or a single-digit day, be sure to put a 0 in front. Okay. Any questions about that or about anything? All right. The last.
The chapter 17 test.
Say that one more time.
Do you know when we'll get the chapter 17 test?
Okay. That is a great question. I was just going to try to address that. We've got a few sections to go for that. We might even finish this tonight. However, that test, just like the chapter 16 test, I've got to retype. And the thing is, since my computer was out and also the internet was out, so I had very limited ability to do anything on the computer because this computer I have now, that was out. That's the one that would have been easy to do. The one that my wife put Windows 10 on, that was a very difficult system. I'm not used to Windows 10, and it was really difficult to get that to operate well and easily. So now that I've got my computer back, I will get back to doing that. I can't swear I have time tonight to put it together because I've got so many papers I need to print this evening, and so I'm going to try to do that this evening. And then tomorrow I'm in class from 8:30 in the morning until 5:45. Well, that's the lab time. So I've got a lab to put together tonight for that class and type it up. So I know that's immediate. I've got to do that. And then I've got to send out all 4 Zoom announcements. So my guess it's probably going to be Friday. However, I've an advisor on Friday, and last Friday, 6 of my 8 half-hour slots were filled already. I've seen a lot of the ones for this week filled, so I don't know when I'll have time on Friday. So it'll probably be Friday afternoon before I even get to start typing that. If I can do it sooner, I will, but as soon as I get it typed, I will put it. Now, what is easier for you? I think I've got to put it out through the messages on Blackboard. And the reason for that is otherwise I have to type in all your names to email it to you, which I had to do today to make the announcement because I couldn't go through Blackboard. But now Blackboard should be up and running again. Oh, and someone new has just come in the class. Hold on a minute and let me see who that is. Taylor is here. So let me admit her and mark her as here. All right. Taylor, are you here yet? Okay, I assume that you are. I see 14 participants. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 names. That's it, because I'm the 14th. All right. Now, what I'm going to do now, I don't know, y'all probably can't see this, but I've got to move this block up here so I can see the screen better. Okay. Now, any other questions? Good question. I'll get it out there as soon as I can. If we don't finish tonight, that takes a little pressure off, but I'll still try to get it out there before we meet next time. So, yeah. Any other questions? All right. Now I'm going to minimize this because it's right in the middle of my screen. And let's get heading. Any other questions? All right, where we left off last time, we're in Chapter 17, Basic Electricity, and we had just got started in 17.6, which is Ohm's Law, okay? And we had talked about who he's from, where it's from. Georg Ohm was the one who developed it. It works for most resistors. Those resistors that work for, they call them ohmic resistors, which sort of makes sense. Those are those whose slope, the relationship between the voltage and amperage, is a constant slope. Okay? There are some materials that are non-ohmic. They do not have a linear relationship. They have a curvilinear relationship. Ohm's law does not work for them. And we got as far as talking about that. I will show you what I mean by linear versus curvilinear. I will see if this works. I started doing this when I didn't have PowerPoint anymore. The graph on your left is a ohmic relationship. The slope between the voltage and the current is a linear slope. The one on the right shows a nonlinear slope. Ohm's law does not work for a material that has a relationship like that between the current and the voltage. Most of the materials, all the ones we'll be dealing with, are ohmic. They will be the straight line relationship. Okay? I didn't want to have to draw the curve, so I just showed you the picture. Okay. What is Ohm's law? It can be written in one of 3 forms. Here is the one they list first. Let me get my pen set up. Come on, it was working before. Here we go. But it's not doing a good job now. There, I've got it. But it's jumping all over the place. I don't know why. Here's one rendition of Ohm's law. I is equal to V over R. And the pen is cutting up again like it did before my computer started messing up. I hope this is not a bad sign. V over R, that other line in there is extraneous. I didn't draw it, it just showed up on the screen. Let me see if I can erase it. It'll erase the whole R. Let me try to write it again. V over R. Okay. Now, what basically that's saying is that the relationship, again, my pen is doing weird things, is equal to, let's see if I can, all the time I was wishing I had my system back, I completely forgot to screwed up like this periodically. For some reason, this is really bad today. Yuck! Everything is real slow with it. Okay. 1 over R you can think of as a constant. It's not. Well, it is for any given resistor times V. 1 over R would be what we call the proportionality constant. The current is proportional to the voltage is proportional to the current. And this is not good news. It says and this is probably what's causing the problem with the pen, our internet is unstable. They just got it back, I mean, a couple of hours ago, and now they're saying it's unstable. This is not good news, but let's go with it as long as we can. Okay, so this is what they mean, a linear relationship. The line here, we've just added another student, I think. I don't know what this 1 more and 2 more stands for. Oh, these are some chats. Let me see what they are. I have no idea what those chats are about. Do you? Okay. We still have 14 people. So no, I thought there were 2 more people coming in, but that's just 2 chats that came from somewhere, probably because the internet's unstable. Okay. So that is what that linear relationship is. This is the slope, 1 over R, between the voltage and the current. Okay. Now, I said this was just one way to express Ohm's law. The other 2 ways would be, one way, multiply both sides by R, and you get V is equal to I times R. Okay, and again, I didn't put that horizontal line in there, and when I erase it, it'll erase most of the R, but that's weird looking. In fact, it erased part of the I and all the R. Okay, it will not write, there it goes, I times R. I swear I'm writing and it's not showing up. There, I times R. Okay, that's another way. In this way, the voltage and the current, again, are directly proportional. This time, R is the constant proportionality constant, if you write it this way. One other way you could write it, solve for R, that would be dividing both sides of this equation by I. So that would give you R. Now my pen is not even showing up. Let me get the pen back. But it's not showing up. Okay, there it came back. Solve for R, divide both sides by I, and you get R is equal to V over I. I said I and wrote R. I don't know what's wrong with my brain. Okay. The pen is incredibly slow right now. Okay. V over I. So those are 3 different forms of Ohm's law. Current is equal to voltage over resistance. Voltage is equal to current times resistance. And resistance is equal to voltage divided by current. All 3 representations of Ohm's law. And they mention at least a couple of these in the text. They do mention one other thing. Sometimes they represent the voltage by E rather than by V. So if you see I is equal to E over R, that's the same Ohm's law. It's just now they're not talking about voltage, which you usually talk about in terms of direct current. If you had, well, not necessarily. You could talk about both in direct current. It's just they call that EMF, which those initials used to stand for electromotive force. That's the source of electrical energy. It's not really a force, so they got away from calling it electromotive force, but they still use the letters EMF. Okay. Why, I'm not sure, but they do. So in terms of units, though, the units for current, does anyone remember? That's the amp. Capital A, because it was named after Louis Ampere. The unit for voltage is volts. The same parameter, same unit, capital V, both of them named after Alessandro Volta. The unit for resistance is an ohm, named after Georg Ohm, but they don't use an O, they use an omega. And I think we talked about that last time. So those would be the units. Current, amps, is equal to volts divided by ohms. Or volts is equal to amps times ohms, or ohms is equal to volts divided by amps. However you wanted to write those. Now, they have a little try this activity. If you want to do that, you certainly can. But actually, to me, that would be a better thing to do a little bit later when we start talking about different types of circuits. So I'm going to leave that off now. We'll probably mention it later. Let's go to example 1. I think I'll erase all this, even though we're going to use those formulas. So hopefully you got the formulas down. Let's go to the... Is there a question? Okay, I can hear some faint talk in the background, but if you're asking me a question, I can't understand it. Was there? Okay. Let's do example 1. A heating element on an electric range operates on 240 volts. Well, that is the voltage. 240 volts. Okay, the parameter is a capital V, the unit is a capital V. One of the few times in physics that those are the same. So here it is. Okay, it has a resistance, that's your R, the parameter R, and that resistance is 30.0 ohms. Okay. Now, interestingly, they did not put a bar over the 0 for the voltage, indicating you only have 2 significant digits there. They did put a 0 after the decimal, indicating you have 3 significant digits there. So the question is, what is the current that it draws? The symbol for current is I. Where they got I have no idea. Voltage V, that makes sense. Resistance R, that makes sense. Current I, have no idea where that came from. Perhaps the French word for current starts with an I. I don't know, because Louis Ampere was French. Maybe that's where it came from. So that's what we're looking for. What is the formula that relates current to voltage and resistance? They were just on the screen. What was the one that gave you what current was in terms of voltage and resistance? Anyone remember? Perfect. Voltage divided by resistance. Okay? And here your voltage is 240. And most of the time I'm a real big stickler for units, and I still am. That would be volts. The only thing here in this situation, you don't see what's canceling out. You just have to remember what the relationships are. Divided by your resistance, which is 30.0 ohms. We talked last time about why they use an omega for ohm. I would say go back and listen to it. You can't. But let me say this in case anyone's maybe a little confused on it. Those days when I could not record, when I wasn't recording with Screencast-O-Matic, when I could not record, what I did then, what I will be doing, I will leave those sessions that we had last term up on the YouTube videos, but they will be up at the top of the list. The ones we're doing for this term will be at the bottom of the list. And where you see a gap in the bottom between, in fact, a lot of chapter 16 was probably missing there and part of 17, those I'll leave from last term. They won't fit exactly, but they'll be fairly close, mostly everything you see. So if you need to go back and review something from a class when I couldn't record, go back and see it from last term when I was able to record, I think, just about everything. All right, let's move on to this. Okay, I'm going to make this a little easier. I'm going to divide both numerator and denominator by 10, which wipes out those two zeros, and you got 24 divided by 3, which is 8. If my pen would write, 8. It doesn't write well, though, does it? That's an 8. And I'm sure they want at least a 0.0. Okay. And the unit for current is what? Anybody remember? Amps. Capital A, amps. Named after Louis Ampere. Okay. So that's what they got in the book. Good for them. 8.0 amps. All right. Any questions on that? I was missing my writable screen until now. I remember what a pain in the neck the pen could be, but I'm still glad we have it so you can see how we work the problems. I think last week when I was working, I was having to type it in, wasn't I? And that was really awful. Okay, so the pen is better than that. So I'm going to erase if there's no more questions and move on to example 2. A flashlight bulb, and let me say this too. I wish I hadn't erased it yet. Heating element, that was what the last problem was. Heating elements, because you hear and you think of term heat in there, that is going to draw a lot of current. And 8 amps is a lot of current. Okay? Here in example 2, we're talking about a flashlight bulb. I will guarantee you it doesn't have nearly as much current. In fact, we're going to see that in just a minute when they tell the problem. Okay, a flashlight bulb is connected to 2 dry cells with an equivalent voltage of 3.0 volts. So the voltage here is 3. That is one ugly 3. I didn't write it that way. The pen is just not picking up and doing its job. Okay. I'll try to write really slowly. 3.0 volts. Okay, that's the voltage. Okay. If it draws, and this is a current because it's amperes, so this is current, I, 15 milliamps. Okay. Now, someone tell me, what do we mean by milliamps? What does the prefix, metric prefix, milli means? That's 1/1000th of an amp. So if you, I don't know if you like just moving decimal places. If you're moving a decimal place, move 3 units to the left, and that would be 0.015. Move that decimal 3 places to the left, you'd have to put a 0 in front, 0.015 amps. Because milli means 1/1000th. You would read that number right there, that decimal number, 15 thousandths of an amp. And that's what milli means, 15 thousandths of an amp. Okay? If you wanted to write it in scientific notation, that would be 1.5 times 10 to the minus 2 amps. That just is a little more awkward. I think that probably, yeah. Nope, they wrote it both ways. They put 15 times 10 to the minus 3 because milli means 10 to the minus 3, or writing that as 0.015 amps. So the question is, what is its resistance? We're looking for the resistance of that flashlight bulb, which didn't draw much current at all. Okay? What formula relates resistance to voltage and current? Anyone remember? Anyone remember?
Divided by current.
Okay, V divided by I. Okay, I'm having to wait until my pen catches up, and it's not doing a good job of catching up. Okay, almost caught up. There it is. That's ugly. Almost as bad as my writing on the other screen. Not quite. So, what is that equal to? Voltage is 3.0 volts divided by 0.015 amps. Okay? Now again here, to do your division, it really makes more sense to move the decimal 3 places to the right here. This is not because of any metric things. This is just how you divide decimal numbers. Oops, need it 3 places to the right. Okay. So that makes a 3,000 in the numerator and a 15 in the denominator. Well, 15 will go into 30, 2, and you have 2 more zeros there, so that's 200 ohms. Resistance is measured in ohms. And since you had 2 significant digits there, 2 significant digits there, we'll make that first zero significant but not the last. So that's 200 ohms, but only that first zero is significant. Of course, the 2 is significant. Okay? And that's exactly how they wrote their answer as well. Now, they mention a thing about electric shock here, and it is pretty important. It's very important. And I know y'all will be working with some electronic equipment, but I'm sure it's going to be very safe, and you probably won't have to worry about shock factors there. But just to emphasize, I think we may have mentioned this in a previous class too, how they used to execute prisoners in the state of Alabama was in the electric chair. Okay? And why they did that, our bodies are electrical machines. If you think about it, all the nerves, the neural endings, all those things that transmit things, they are electrical in nature. You're hearing me speak, that's because your ears, we talked about the ears before, they connect to the auditory nerves that haul the signals off to the brain, electrical currents. Your vision, you're seeing this on the screen. In the back of your eye bulb, you've got a screen there that changes light into electrical signal. And then you've got nerves that haul that to the brain, and your brain interprets it. I mean, we are complex electrical machines that run at incredibly fast speeds, because you don't have to think about what you're seeing. You see it and you realize what's going on. It's pretty amazing, our thing. Well, and guess what? Your brain, believe it or not, a part of your brain, it's called the autonomic nervous system, is telling your heart to beat every time it beats. It wouldn't beat on its own. It has to receive that impulse, and that's an electrical signal that's telling it contract, contract. And in fact, it's more complicated than that. Your auricle, or I think that's can't remember. Ventricle is the lower part. Auricle, I think, is the upper part. Those are beating slightly at different rates. I mean, not same rate, but at different frequency, different times. So let me just put it that way, of each other. One beats first, then the other. It's a thump-thump, thump-thump, thump-thump. That's a healthy heart rate. Your brain is telling it to keep it in that rhythm. Okay? The auricle is just a fraction of a second ahead of the ventricle, okay? And actually on the two sides of your heart, they may be going at slightly different rates. It's just amazing how we do, and it's going on 24/7, okay? Everything you do is electrical, okay? Well, what the electric chair did was send a lot of current through that system. Now, your system, your electrical system, your body runs on very, very, very low current. We talked here about milliamps. We're talking in your body probably microamps or smaller, okay? So it's not much current. That means not a big potential difference. The resistance is fairly low, so you don't need a lot of potential difference. That electric chair sent tons of voltage, a big potential difference, sent tons of current through the prisoner's body. That's what killed him. Not a very humane way of executing prisoners, but that's what they used to do. Because guess what? Your body is an electrical machine that completely overpowered. Well, that's the same thing that happens when you get shocked. Okay, you don't want to get shocked by something that's producing a lot of current. You do not want that to happen. That would be almost the same as an electrocution. Okay, minor shocks, you can just feel them, and your body immediately will pull away from that. Okay, so trust your body. In fact, you don't have any control. It does it automatically because it's a very good electrical machine. But it is something to keep in mind. All right, that's enough said on there. This finishes 17.6. You have some problems at the end of this section on page 467. Do any of the odds 1 through 13 that are in the back of the book, and then probably turn over and do 15 that's in the back of if it's in the back of the book too. All right. The next topic here is going to be a series circuit. And I want to use the illustration from the book. I want to use the illustration, there it goes, to help with this. So I'm going to this other display, and we'll go from current slide here. And this is what you see in figure 1726 on page 468. And I will try to point what's going on here. This is a series circuit. And what does that mean? Now, this is done as if it's a battery. This would also be applicable if you were, and a battery is direct current, if you were alternating current. Same deal, okay? But let's just say, now they're saying they don't tell you which phase of the battery you're going from. Let's say this is the positive side, and this is the negative side. The way they've drawn it, that's what it appears, because you see the positive here. So you're going first, let's see this, oops, we lost somebody. They'll probably need to come back in, so y'all let me know if you see any indication someone's trying to get back in the course. Because we did lose someone and maybe a signal went out. Now, I understand it's already happened once that my internet strength was a little low, so hopefully we're not about to lose that again. Okay, but here we go. The current leaves the battery and goes through the load, that's the light bulb. And depending on what kind of light bulb that is, it kind of looks like an incandescent bulb. If it is, then that means that you're heating up a filament, so you're sending a lot of current, a fair amount of current through there to heat the filament, and the bulb has a fairly large resistance. That light bulb we just did was a 200 ohm resistor. This is probably at least that. And then it leaves there, goes through the switch. Now, guess what? If that switch is open like this, not a bit of current is going to go through that bulb. That switch has to be closed to complete the circuit so that the current will start flowing. And then they show here, and this is called conventional current. Now, I don't know why that came up. I don't know if y'all could see it, but it did. It didn't look like anyone was trying to add to the course, but it just popped up. So there is what we call the circuit diagram here. This is actually a physical diagram of what the circuit's about. The battery is represented by two parallel bars. We lost somebody else, it looks like. Okay? I hope it's not because my internet is breaking up. I can't tell that it is, but anytime they start making signals like that, it worries me. So a battery is represented by two parallel bars. The positive is usually the longer bar, the negative is the shorter bar. So therefore the current is going to go from high potential to low potential, and that's why they drew the current going in that direction. The load is down here. Often the load is represented by a jagged line like this, and that's called a resistor. The load is a resistor. Here's the switch. Most of the time I consider the switch closed, otherwise it wouldn't be a current. So let's just pretend that's closed, otherwise there would be no current. If the switch was open, there would not be a current, so they would have that mislabeled. Okay? That's a parallel circuit. What do we mean by that? A series circuit. We mean that the same current goes through every element in the circuit. Okay? There is one pathway. So that current goes through the load, it goes through the switch, it goes from the battery, through the battery, and out again. Okay? The same current goes through every element in the thing because there's only one pathway for it to go. And remember, we talked about this before too. Your load here is not using current. It's using the energy that that current is carrying. Well, the energy came from the battery. That's why it's called the source. That's the energy source. So the battery gives it the charges energy, and then the load uses that electrical energy and changes it to heat energy or light energy, some other type of energy. It could be heat energy if that was a burner on your stove. It could be sound energy if that was a radio. It could be whatever kind of energy had. Maybe kinetic energy if it was a toy that motored itself around the room. Okay? Or the vacuum cleaner, or anything such as that. Okay, that's your circuit diagram for a series circuit. The same, there's only one pathway, and all the current goes through all the elements in that circuit. Okay. In your text, you saw the symbol for resistance there. I don't see my picture anymore, so I don't know if I'm even being shown here, but this is well, I can't tell if it's there or not, so I can't show it to you. So anyway, it's in your text if you've got it. Now, this is an equation that shows up at the top of at the end of this section. So there's going to be a lot of things that happen before there. So I'm going back to the white page so I can deal from there. And there's my picture again. Okay, we'll go from current slide. And let me just check to see if anyone's waiting. I don't see anyone waiting. Okay. Here is the series circuit at the bottom of the page. Now they're indicating here perhaps a more powerful battery than the last one did because they're doing long bar, short bar, long bar, short bar. That's suggesting it's a 2-cell battery. The other one is just a single cell. You can put whatever you want to there. The current is leaving here, and they give the current moving like this. There's your I. This, by the way, is your, they're calling this E now. Either E or I, E or V, whichever you want to call it, they're calling it E now. Before they were calling it V, okay? But they mentioned that you could call it either way. Up here, and this doesn't matter where it is, you hit a resistor, okay? Then you hit another resistor. Then you hit another resistor. And then you make your way back to the battery. Now these could be one on that leg, one on this leg, one on that leg. You could have drawn it any way you wanted to. I just did it the way the book did. Now, they're saying the total current is leaving the battery right there, and that's true. And here's a resistor here, R1. Okay? Now, they're putting another current here and calling it I1. Okay? And they're putting another current here after this resistor. This resistor is R2. And they're putting another current here, I2. And then they name this resistor R3 and put another current leaving this and called that I3. And that's what makes its way back to the battery. Now, they also show that you have a voltage drop here, and they're calling that V1, and another voltage drop here, calling that V2, and another voltage drop here, calling that V3. Okay? In other words, they put a little voltmeter across each one of those resistors separately, and you're measuring the voltage that dropped across there. Now, based on what I said before, what's the relationship between I1, I2, I3, and I? Remember what I said was true of a series circuit? The same current has to flow through everything. So this is saying I1 equals I2 equals I3, and that's equal to I. That's the same current throughout. You don't use up current in a resistor. You use the energy from that current, but you don't use the current. Okay? So the current's the same. There's no reason for the subscripts 1, 2, and 3 there. There's none. Okay. Now, the voltage, however, you have one drop here. You have another drop there, because remember what voltage is? Voltage is equal to energy. I'm going to put joules because I use E over here, per coulomb. That's what a volt is. How much energy is given to each charge? Well, that's what's being used by the resistors. So this would be the energy used by that resistor. This would be the energy used by that resistor. This would be related to the energy used by that resistor. So in effect, you can now say V1, the voltage drop across resistor 1, plus the voltage drop across resistor 2, plus the voltage drop across resistor 3, that's equal to the total voltage, or E, whichever you want to call it, of the whole battery over here. This is giving the energy to the charges. This is using up those. And you use up exactly what you give. Okay? Now, with that in mind, and since we know that V is equal to IR, but all the I's are the same, then this is saying this would be I times R1 plus I, because it's the same current, times R2 plus I times R3, and that's equal to the total voltage of the battery, or you can call that E, whichever you want to call it. Well, guess what? The I's are the same. You could factor those out and just say I, and then this would be R1 plus R2 plus R3, once you factored out the I, and that's equal to the voltage, or E, or whatever you want to call it. That's not energy, that's electromotive EMF. Okay? Well, guess what? This is what we call the equivalent or effective voltage of the whole system. I mean, effective resistance. And that leads to the third formula. I1 equal I2 equal I3 equals I. V1 plus V2 plus V3 equals V, or E. And then for the resistors, your total resistance of the system, and they call it just R. I usually call it effective resistance or total resistance, I sub E or I sub T, is equal to R1 plus R2 plus R3. For a 3, well, that's a R, R3. For a 3 resistor system, that's what you got. So for a series circuit, the currents are the same, the voltage drops across each resistor add, and the individual resistances add to give you your total resistance of the system. Okay? So those are the features of a series circuit. I tried to get my eraser and it didn't come up. Okay, that looks a little better. All right. And that was what they said in that summary statement that I had on the slide earlier. We'll pick that up a bit later. Let's do the examples first. Okay? Now, so let's pick up with example 1. Okay. I'll clear the screen. Any question on it before I lose it? Okay, I think we lost another student. Okay, we're down to 11. I'm one of them. Okay. So we'll erase all that and do example 1. Find the total resistance of the circuit shown in figure 1728. Now I wish I hadn't erased what I just had written, because I could have just used the same one because it looks just like it. They put a 2-cell battery here, not that that matters any. And then they went through resistor 1, resistor 2, resistor 3, and back to the battery again. Okay? They told you R1 was 7.00 ohms. R2, this time they told you, was 9.00 ohms. And R3 over here is a bigger resistor that's 21.0 ohms. Okay? Now, it says find the total resistance of the circuit. Okay. Now, remember, I keep saying this and there's a reason. This is a series circuit. The total resistance of a series circuit is going to be different from that of the total resistance of a parallel circuit or a combination circuit, which we'll do last. We're just going to focus on series now. So what is that total resistance, which we call R? What was that formula I just had up there? What you do with your resistances in a series circuit? You add them together. So that would be 7.00 ohms plus 9.00 ohms plus 21.0 ohms. Okay? Well, I know that 21 plus 9 is going to be 30, plus another 7 is going to be 37.0, 3 significant digit ohms. Actually, the more important thing is this is to the nearest tenth, the other nearest hundredth, we round to the nearest tenth. So that's 37.0 ohms. Does that make sense? That was a pretty simple problem. Just add them together. Okay? Now, this time I'm going to pay attention to what my thing, but it's still not going to help me any. I'm going to have to redraw. Okay? Whoops. Okay. Yeah, redraw most of it anyway. Okay, this time this is example 2. And by the way, all these things are going to change too, so let me get rid of those. And we'll get rid of these. And we'll add one more. Okay. We'll get there in a minute. So here's your circuit. Resistor 1, resistor 2, resistor 3, coming around, and then have a resistor 4 down here. Doesn't matter where you put them. And there they are. So here's R4. Okay, this time R1, on this time they told us the E, or V, whichever you want to call it, is 90.0 volts. Now, they draw that as if that's a battery. And it may be a battery, but you don't find many batteries that are 90 volts. Your car battery is 12 volts approximately. A tractor, big heavy tractor, may have a 24 volt battery. And something like a bulldozer or something really big like that might even have a 36-volt battery. I've never seen a battery that's 90 volts. Maybe there are. I don't know. Do any of you have electric cars? I don't. Maybe their batteries are really big like that. I don't know. But most of the time, if you have a big number like that, that's alternating current, and they use the wrong symbol. But it's okay. All we're interested in, that's the voltage. Okay? The R1 here, they say, is 5.00 ohms. R2 here, they say, is 13.0 ohms. R3 here, they say, is 12.0 ohms. And R4 down here, my goodness, is a 96.0 ohm resistor. Okay? A big one. And they show that the current is flowing like this, which is correct. It goes from high potential, the plus side here, to low potential, the minus side. Now, in reality, we call that conventional current. That is different from electron current because electrons are negatively charged and they would go in the other direction, okay? But we usually talk about conventional current. Okay, I'm going to change this to, okay. We're not doing that yet, but we're going to, okay? So here are our 4 resistors and our voltage. What do you think they're going to be looking for? The current. That's the one thing that didn't have a unit given to it. So, how are we going to determine current? Whose law might we use?
Ohm's law.
Ohm's law, of course. But to do Ohm's law, you need to know what I call the effective resistance. The book calls total resistance. Both of those are good names. You need to know the R, not any one of these R's, the entire R. So that's why at the bottom, I left that formula up here. What is your total resistor? What would it be? 5.00 ohms plus 13.0 ohms plus 12.0 ohms plus 96.0 ohms. What does that add to? No super easy, yeah, it is an easy way. 12 and 13 are 25. Add 5 to that, you get 30. Add that to 96, and you get 126. 126 ohms in that circuit. That's how much resistance that circuit has. Okay? So now that you know the total resistance, what Ohm's law form would you use?
I equals V over R.
Okay, V over R, in this case E over R. E and V are the same. Okay, E over R, and that would be 90 volts, 90.0 volts divided by your 126 ohms. Okay, and what would be that current? Calculator time, right? I won't do that one in my head. I can't find it. There it is. Thought y'all would already have it before I even got it typed in. What did you get? Anybody? 90 divided by 126. 0.714 ounce. Now, if you don't like having a decimal number there, you could call that, moving the decimal 3 places to the right, that would be 714 milliamps. I don't see any difference. I think I'd leave it 0.714 ounce. Just harder to say. Or 714 milliamps. That's pretty easy too. But that's absolutely correct. The book left it 0.714 ounce. Okay. So there, example 1, we just calculated resistance by adding 3 resistances together. This one, you had to do this with 4 resistors, but you only did that as an intermediate step so you could calculate your current. Example 3, on the other hand, you're going to figure out what resistance you need to put in there to give you a given current and voltage. And rather than try to reuse this again, I think I'll go on and delete it and draw a new one. So here's your good old battery, same one we had before. No, it's not the same one, because this E is 115 volts. That one I can almost guarantee you would have to be a alternating current. I've never seen a 115 volt battery that I know of. But anyway, it leaves here and goes through first the first resistor, R1, goes through the second resistor, R2, third resistor, R3, and then goes back to the battery. Okay? It shows the current flowing in this direction, which is absolutely correct. And that I here is 3.00 amps. A good unit for current. So a lot of voltage, not a whole lot of current, so I would guess this must have a fairly high resistance. Let's see. R1 would be 23.0 ohms. R2 is 14.0 ohms. And R3 down here is, oh, that's what we don't know. That's the unknown here. What current, resistance must you have in that third resistor in order to create a current of 3 amps with 115 volt, what they call power supply? It's really an energy supply, but they call it a power supply. Okay. How would you go about doing this? Whose law might you use? I think that's a pretty easy question. Ohm's law. Now, since we're looking for a resistor and we know voltage and current, how would you express Ohm's law for this problem? What you're looking for is the resistance, and that's equal to what? The two things we know, but where do you put them?
R equals V over I.
V over I, perfect. And that would be 115 volts divided by 3.00 amps. Okay? So what would be your total or effective resistance of this circuit? Okay? Well, that's not going to go in even amount. So let's see what it does. 115 divided by 3 equal, what would you write down there? Did y'all punch it in? That is how violent we Southerners are. You punch it in, don't you? 38.3, what units? Resistance. What units? Someone say it?
Ohms.
Ohms, of course. Okay. Now, that's your total resistance. But we also know that the total resistance is equal to the sum of your individual resistance in a series circuit. And this is a series circuit. The same current flows through every element. Okay? So this will be R1 plus R2 plus R3. Right? Series circuit. That's the rule. Okay? You know your total resistance is 38.3 ohms, and that's equal to 23.0 ohms plus 14.0 ohms plus R3, which we don't know. So how are we going to determine R3?
Correct?
Yes.
Solve out the formula.
Right. Yeah, I think I would add these two first. Those add to be 37.0 ohms. And then I'd subtract that from here. And what do you have left? R3 is equal to a paltry little, how much? 1.3 ohms. Really small resistor in order to get that amount of current. Okay? Because those were two big resistors there. You didn't need much more resistance to make that happen. And that's exactly what they did. They got 1.3 ohm resistor. Does that make sense?
Yes.
Okay. Now, the next question is, referring to this very same figure here, find the voltage drop across R3. So what we're looking for is, what is the voltage drop that goes across here? What's your V3 that goes across here? We lost somebody else, didn't we? We're down to 9 students, plus me makes 10. Okay? So how do we find that resistor? That voltage. The voltage drop there. You tell me. I wonder whose law we'll use.
Ohms.
Ohm's law. And how does it go if we're looking for voltage? V3 is equal to IR. So that would be I. The same current goes through everything, so you don't have an I3. It's just I times R3. Well, your I was 3.00 amps. Multiply that by R3, which we found was a paltry little 1.3 ohms. And what was the voltage drop across that resistor? 3.9 volts. Right? 3 times 1.3 is 3.9, and amps times ohms equal volts. Does that make sense? Okay.
Yes.
All right. Now I'm going to... Does anyone need this left up here a little longer? I know there's a lot of writing on there, and I'm all over the place. But do you see how that works? Okay. What I'm going to do then, if no one needs it longer, I'm going to escape and go back to this slide. Quit. Okay. And go back to where we started here. This is the summary characteristics of a series circuit. The same ones we listed earlier. Your current through each resistor is the same, because a series circuit only has one pathway. Current is neither created nor destroyed. Charges are neither created nor destroyed, so you have the same current going through everything. Okay? So I is equal to I1 is equal to I2 is equal to I3. Same current goes through everything. However, the resistances in a series circuit, remember this is a series circuit, those add. Okay? So the R is the effective or total resistance. It's R1 plus R2 plus R3 plus as many R's as you have in series with each other, meaning they're all connected by one pathway. The voltages, the total voltage supplied by the battery has to equal the voltage drop across each resistor. So E, the voltage supplied by the battery, is equal to V1 plus V2 plus V3. As many as you have, those are the voltage drops across each resistor. They add to be the total voltage supplied by the battery. That's where it comes from. That's where the energy per unit charge comes from. Okay. And that ends 17.7. There are some problems here. I would do any of the odds 1 through 5 that are in the back of the book. Number either 7 or 9 if they're in the back of the book, and I think they are. And then 11 or 13 if they're in the back of the books. Okay. quite a few circuit diagrams there. Be sure you're looking at the right one for your problem. Okay? Now, let's move on to parallel circuits. So let's see what we have next. Here it is. This is what we call a parallel circuit. Now, there's several ways you can represent those. Here's the deal with a parallel circuit. You've got a power supply here, a voltage source. That's your E or your V, whatever you want to call it. But in this case, your current that leaves here, that's your I, some of it goes through this resistor. We'll call that I1, and that is different from the current that goes through this resistor. That's I2, and that's different from the current that goes through this resistor, which is I3. Here's why they have to be different. Because at this node, some of the charges go this way, others keep going here. Some of those break off and go here, the rest of them go here. So you have three different currents here, one voltage supply, okay? And these three currents add to be your total current in the system, okay? Now, here's the, you might find surprising part. If you've put a voltmeter across this battery, that would read what the voltage of the battery was. Let's just say 6 volts, okay, across there. Well, you put that same one, a power supply, a voltage meter across here between points A and B, and guess what? You're still measuring across the same 2 points. That's still a 6 volt drop. And guess what? Here to here is still a 6 volt drop. And here to here is still a 6 volt drop, because you got nothing in between, no resistors in between there. That's still a 6 volt drop. Okay? The currents add, the voltages across each resistor in a parallel circuit are always the same. And they're the same as the voltage across the battery. Okay? Same thing goes here. Your current that leaves here, part of it goes up this way. That would be your I1. Part of it goes through here. That's I2. And part of it goes down here. That's I3. This is the same circuit, just drawn a different way. And guess what? You put a voltage meter across there. You measure the voltage of that battery. I said 6 volts, whatever it happens to be. Now, we're going to assume that the switch is closed, because otherwise you don't have any current at all. But if the switch is closed, then the current here adds to those 3 currents. But the voltage drop across here is the same as the voltage drop across there, because there's no more resistance in between this point and that point, or between this point and that point. No resistance, so the same voltage across those. So the same voltage across that current resistor, that one, and that one. All your voltage drops are the same, and they're the same as your battery. Okay? Sort of get the idea? You see what's majorly different here. Now, the interesting, really interesting part of a parallel circuit is what your resistors do. We said what the current does. The current breaks into 3 individual currents, I1 plus I2 plus I3 make up I. And we know what the voltage does. It's the same across everything in a parallel circuit. But we haven't said what goes on with the resistors. Okay? So, let's see what they do. Well, they're going to do the pump model. We'll come back to that later. I'll just write it here. I've already said it, that I is equal to I1 plus I2 plus I3. That's the I3. Okay, let me erase that ugly P-looking thing in there. Okay. Now, I don't know if you've noticed my pen's doing much better now. I'm guessing that's because our signal is better. I don't know that for a fact, but that's what I'm guessing. Okay. Now, in a parallel, and this is parallel. Remember, this is a parallel circuit. The V, or the E, is equal to V1, is equal to V2, is equal to V3. For all those voltages, it's the same voltage drop across each resistor because it's a parallel circuit. There are different pathways the current can take, but it's the same voltage across each one. Okay. Now, here is the crazy part. If you think about what current is voltage over resistance, right? And that would be V1, which is still voltage, over R1, which is added to this current here, V, which is same voltage, over R2, which is same voltage over R3. And if you factor out the voltage, because they're all the same, so divide them out, and those just become ones then. So here's what the relationship is for your resistors. In a parallel circuit, 1 over the total or effective resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, okay, that looks reasonable. Here is the part I think is really, in some sense, it's sort of amazing till you really think about it. If you were to put numbers in that, because they're in denominators, you'll find out if you put bigger numbers in R1, R2, and R3, your R winds up being less than any of them. So the more resistors you put in a parallel circuit, the overall resistance actually decreases, not increases. Now that doesn't sound like it makes any sense at all, but indeed it does. Because what it's doing, it's requiring that battery to supply more and more current. Because every time you put another resistor there, the voltage stays the same, and the current has to increase because you put another resistor there. So you're increasing your current, which is effectively decreasing the resistance because those are associated in a inverse relationship. So this is your key for resistors in a parallel circuit. It's a lot harder to work with the numbers, and I'll show you some shortcuts. They're going to break it back down to a 2 system. So I think I'll get out of this time and go back to my white slide. Okay, white page here. Now I'll have to find my pen again. Okay. Let's go back to a 2 resistor system. 1 over R is equal to 1 over R1 plus 1 over R2. Okay. Now, whatever those R's are down there, what if you're trying to add fractions like that? Well, you'd have to have least common denominator. Well, the common denominator would be R1 times R2. So that would be R1, R2 plus R1, R2. Now, you had a 1 up here over R1. To get the common denominator of R2, you'd have to multiply this by R2. You had a 1 here. It was a R2 down here. To get an R1 here, you'd have to multiply by R1. So that gives you R2 plus, we're down to 9, and we're losing them like flies, okay, plus R1 over the product of R1, R2. Now this gives you 1 over R. So to get R, you have to reciprocate. Flip that over, you flip this over. R2 times R1 over R2 plus R1. Now you could put them R1 plus R2 and R1 times R2. It doesn't matter because both multiplication and addition are commutative, so it doesn't really matter. But what you see there, the product of those resistors divided by the sum. And if those are very large resistors, the product's going to be way bigger than the sum. So guess what? Well, let's see, did I say that right? it's going to be somewhat bigger. And your effective resistance is actually going to be less than any one of them. You don't really see that, but indeed that's what you get. Okay. Now, that's what we mean by effective resistance. Now, they drew the pictures over here, and if this was your E, and these were your resistors, R1 and R2. Okay? So if this is R1, this is R2. The E is the same for both. Okay. Now, if you replace these two with one resistor, so draw the same thing, same E, but now we're going to replace it with one resistor. This E is the same, and here's your R. That resistor is actually going to be less than either one of those two, because you got the same current flowing through here, I and I, same current flowing through. Well, part of this current goes to I1, and part of this goes to I2, and that if that was one resistor here, you got more current going through the same resistor to give you the same voltage, so that means the resistor has to be less, okay, because of the inverse relationship. More current, less resistance, okay. That, I don't think, shows it that well, but that's what they were trying to get to by that figure. Now, but it's true, and we'll do it with numbers in a little bit. So let's go back to our pump analogy, which was over here. The next slide down, we'll go from current slide. And this, hopefully, will give you a general idea of what we're talking about. The pump is like the battery. Remember, we did a water analogy before. The pump is like a battery. Okay, that's what gives the energy to the water. The current is like the flow of the water. Well, current is flow of charge. Charge per unit time. That's the flow of like the flow of the water. Well, if you put one resistor down here, that would be a small pipe here, another small pipe here, another small pipe here. You got some current, some water flowing through here, some through here, and some through there. If they're different sized pipe, different amount of water is going to flow through. But to get the total water through, you would need a bigger pipe. If you replace this with a pipe, you'd have to have the pipe the same size as these pipes, which would be bigger than any one of those. So less resistance. The bigger the pipe, the less the resistance. These are small pipes, so they have great resistances. A bigger pipe has less, and you only have one of them. So that's the water analogy. Same current going in and out of the pump, but they breaks up into smaller, and that's why you have different currents going through each resistor, but the resistance is added by reciprocals, 1 over. All right. All that said, let's go to, there's a summary slide. We'll come back to that a little bit later. Let's go to the white page again. Before, I couldn't do this because it was, well, I don't know. Y'all didn't see me on the iPad. That was horrendous. Okay. Good iPad, and it was the only thing we could get to work, but boy, that was tough. Find the equivalent resistance of the circuit shown in 1743. That shows, let me get my pen back. Okay. A battery here, or a power supply, whatever you want to call it. They don't give it size. Okay? And they show a resistor here, R1, another resistor here, R2, and another resistor here, D2, no, R3. Okay, so this was R1, and that was 7.00 ohms. Here's R2, and that was 9.00 ohms. And here's R3, and that was 12.0 ohms. Okay? Now, without knowing any current, without knowing any voltage, we've got to just work resistance. What is the effective resistance, the R, of this circuit? Okay? Now, what's the formula that governs that? Remember, it's all reciprocals. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And plugging in the numbers we have, 1 over 7.00 ohms plus 1 over 9.00 ohms plus 1 over 12.0 ohms. Now, I'm so glad that I don't have to do that by hand. That 1/7 really throws everything off. So I'm going to walk you through how to do this on your calculator, okay? All right. Now I'm going to turn my calculator like this, sideways, so I can get the more complicated. I don't know, can you see my calculator there? Yes or no? Do I go up or down, right or left, forward or back? Anybody? You can see it? Okay. I'm not holding it very steady, am I? Okay, how you enter this, okay? Here's how I would say. I wouldn't do 1 over 7. Here's the easy way. Just type in the 7. I don't know if you can see it. Press the 7, and then look for the key, and it may be different on your calculator. But on my calculator here, it's 1 over x. It's right over here on the far left side, the third row down, 1 over x. On some of your calculators, on mine it's a 1 over x key. Some calculators will be x to the -1 key. One of those two buttons, that's what you look for. Do all of you find that on your calculator? One of those two buttons?
Yes.
Yes, okay. So after you press 7, then do the 1 over x key, or the x to the -1. And then do your plus, and then enter your 9. And then your 1 over x key. And then we do another plus, and enter the 12. And do the 1 over x key. And then I'm going to press equal. That's not your R. That's 1 over R. So to get that, I do the 1 over x key one more time, and that gives me an effective resistance. R effective is equal to, approximately equal to 2.96 ohms. Do y'all get that?
Yes.
You did? Excellent. That 1 over x key, or x to the -1 key, that makes these reciprocals so easy to do. But the thing that people will forget to do, they'll do it for the 7, 1 over x, 9 plus 9, 1 over x, plus 12, 1 over x, equal, and it will write down that answer. That's not the answer. You have to do one more 1 over x to get the R. So don't forget that last point. Okay? Now, here's the other way to remember this. Notice what your resistors were individually: 7, 9, and 12. Guess what the effective resistance is? Less than 3. Less than the least of those. So if you ever give me a resistance in a parallel circuit, the effective resistance of a parallel circuit that's greater than one of the entry individual resistances, you've done it wrong. It always has to be less than the least of those input resistances. Does that make sense? It may not make sense, but do you understand it? Or at least the concept. Okay? I'm going to get my calculator back. Whoops, I should have zeroed it first, but that's all right. Okay. There was example 1, and they got 2.96 as well. Now, at the top of the next page, they show that same, I can't see holding it up there. I hope you got your books open. Top of page 475, they show those keys. 7, and they don't have the 1 over x key, they have x to the minus 1. Same thing. X to the minus 1 plus 9, x to the minus 1 plus 12, x to the minus 1 equal, and then do another x to the minus 1. We didn't have to do the last equal. It already popped up for us. 2.96470, blah, blah, blah. We don't write all those down. 3 significant digits to each one of those. So round, look, 3 digits, 2, 9, 6. Look to the right, 4, that's less than 5. Drop the rest of them. Leave it 2.96. All right, does that make sense?
Yeah.
All right. Now we're going to move to example 2, which is it's almost the same circuit. It's just got different resistors, so I'm going to draw it. But they draw them differently, and that's fine too. You can draw them any way you want to as long as they're all parallel. So I'm going to erase this one. Okay? And I'll draw it the way they did. Here's the battery, or the power supply, the EMF, whatever you want to call it. They're calling it E. I'll call it E2, just so we'll be consistent. 90.0 volts, which I find is incredibly large for a battery, but we'll do it. Certainly a 2-cell battery. That's not a 2-cell battery. That's way bigger than that. Okay. Now it comes over here, and part of it goes up to resistor 1. Part of it goes through to resistor 2. And part of it goes down here to resistor 3. Okay? This really is the same circuit we had before, just different resistors. They just drew it differently here. To me, all of them, they look parallel. That's why they call them parallel resistors. Okay? And they have the R1 up here equal to 23.0 ohms. Now, I saw something pop up. Oh, we lost somebody else. I keep checking just to make sure no one's trying to get back in or no new person's coming in. All right. R2 down here in the middle, we're going to call, or they give us a 14.0 ohms. And R3 down here at the bottom, they've given us to us as 5.00 ohms. Doing that just to make sure all of them have 3 significant digits. Okay. Now, one thing they didn't say here, and what was that? What are we missing? We got voltage, we got resistance. What are we missing? I. That's, yes, in Navy speak. There we have our I. Now, that I is the same here as it is there, but it's not the same here. This would be an I1, this would be an I2, and this would be an I3. Okay, we may not need those, but that's what we're missing from the circuit. But no, those are different currents through each resistor. We may not need them. I think all we're going to be, let's see what the question is, maybe that would help. Find the total current in the circuit shown. So we're not interested in the individual, we're only interested in the total current. Okay? And that's actually a little bit easier, perhaps. What do you think you're going to have to do first? What law are you going to use to get total current? Ohm's law. And how does that go if you're looking for current? So you're looking for I. What is I? Ohm's law.
I equals V over R.
V over R. Perfect. Now that R is your total resistance, your effective resistance. It's not any one of those individual resistors. So the first thing you've got to do here is find out what that R is. Or actually, now this is a little sneaky here, you're really looking for 1 over r, aren't you? That's the same as v times 1 over r. That's v over r, right? We can calculate 1 over r. This time we're not have to change. They didn't ask what the effective resistance. They just want to know what 1 over r is, because you can just plug it in here, multiply it by 90. So let's do that. We won't do that last 1 over x, okay? Or x to the minus 1. We'll just do this. So what would be 1 over r? Help me. 1 over 23.0 ohms plus 1 over 14.0, I can't write, ohms plus 1 over 5.00 ohms. Okay? This time we're going to use that same little strategy we used before, our reciprocal keys. Got to wake up my calculator on my phone again. Okay? Alright. So, I'll flip it over to the side here and just type in 23 1 over x plus 14. Whoops, that didn't enter right. 14 1 over x plus 5 1 over x equal. Something's wrong with that picture, I think. Maybe not. Now, I have big fingers and these are little keys, so I may have hit something that came in wrong. This shows, what did y'all get? Don't do the 1 over r at the end, the 1 over x at the end. I get 90.0 volts times 1 over r, which my calculator is telling me is 0.319 blah, 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 blah. So I'm just going to multiply this by 90 and see what we get.
I got 0.315.
I did too. And then when you multiply that by 90, what do you get? .3. This is a measure of current. That would be amps. Let's see if that's what the book got. Oh my goodness. Yes, it was. 28.3 amps. Now we didn't find the effective resistance. We stopped at 1 over r because that's all we needed here. We could have calculated 1 over r and then the V divided by that, but why do that? We already had this number, 3.319 blah, 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 on my screen. Multiply that by 90 and you get 28.3 blah, 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 okay? But we're only interested in 3 significant digits because we have 3 significant digits for the voltage. We have 3 significant digits for each of the resistances, so why not have that for the current as well? That's what they got. Good deal. Any questions?
Why did you not press 1 over x again at the end?
Well, just because I wanted 1 over r, and that gave it to me. You could have done the 1 over x again, and when you did that, I don't have it on the screen anymore, you would have gotten some number, and then you do V divided by that number, r. And that would have given you the same answer. If you did it that way, do V divided by R. 90 divided by that resistance you get, I think you'll get the same number, 28.3. In fact, that's what the book did. They did the 1 over R and got 3.18 ohms, then divide 90 by 3.18, you get 28.3. I was just being lazy. Sorry about that. No, I'm not. I'm just lazy. So rather than doing 2 more keystrokes, I just did 1. Okay, I left it at 1 over R and then multiplied that by the voltage of 90. You can go on and do the 1 over X at the end, give you R, then you do V divided by R, and that gave you the same answer. Okay? That wasn't probably a very good answer to your question, but is that okay?
Yeah, I was just confused because the last one we hit 1 over x, but this time we didn't, so I just wanted to know why.
To get the effective resistance, if they had asked for that, for sure that's what you would have done. It's just this one. They didn't ask for it, so I didn't do the extra step to get it. I just took that 1 over R and multiplied it by V, and that gave me the same answer. If you'd have done the extra step, then V divided by that R, 3.18, I think it was, you would have gotten exactly the same answer. Just whether you want to do an extra keystroke up there and then one more keystroke down there. It's fine. You'd have to enter the number too. All right. Any other questions?
The other one was asking for effective resistance, and this one was total resistance. Is that why?
Okay, yeah, total resistance, effective resistance, they mean the same thing. I call it effective resistance. The book, I think, calls it total resistance. It's just that, to me, the word total makes it sound like it's more than the other pieces. It's not. It's less than the other pieces. So therefore, I like to use effective resistance because that doesn't imply you're increasing the resistance. It just says, what is your effective? What is that replacing? What little resistor could you put in there to replace those 3 big ones? And that would have been 3.18 ohms, less than any one of those. Okay? Did that get your comment?
Yeah.
Okay, great. All right. I think we've got time to do example 3. Let's try. Okay? Bottom of page 475 goes to the top of 476, I think. Yeah. Okay. Find the current through R2. Okay, is this the same one? Yes, yes, yes. Thank you for not letting me erase that. Okay. We're looking for the current that goes through that 14 ohm resistor. Oh, yeah. This isn't too bad. The current, the I2 that goes through that resistor. I wonder whose law we'll use. Anybody? Ohm's law, of course. Okay? And Ohm's law states current I2 is equal to what? What is your current equal to? A little louder. Ohm's law. When you solve for current, what's it equal to? Help me, somebody. I is equal to?
Is it for the equation?
Yeah, the equation.
I equals V over R, or
V over R. And because we're doing with R2, we'll put R2 down here. We're doing I2. Okay. Now. No, wait a minute. I've got it backwards. Sorry. No wonder you were saying, what is this guy doing? We're looking for R2. No? No, I was right. Find the current. Yeah, I'm sorry. I had it right. It must be getting late and I'm getting hungry. Okay. I2 is equal to V over R2. You said it right. Okay. Now, we know what the voltage is, don't we? 90.0 volts. Because the voltmeter anywhere across that circuit is going to read 90. Divided by the resistor of R2, and that was 14.0 ohms. So what's your R2? Sorry.
I got 6.43.
That sounds pretty good. Let me see what I get. 90 divided by 14 equals 6.43. I love it. Okay. 6.43 what?
Amp.
Yes, 6.43 amps. Now, does that make sense? Yes. The total current in the system was 28.3 amps. That's what we got before. So these, the currents through these, have to be less than that because this is what splits and goes to that. And the one in the middle is the middle one, so that's going to be more current that goes through the top one because that has more resistance, but a lot less current than the one on the bottom because that has the least resistance. So that looks reasonable, 6.43 amps, and that's exactly what they get. Okay. Now, do we have time for example 4? Oh, and that's a different figure. Let's see. I think we got 4 minutes, 3 minutes. I don't think we'll quite make it. So let's plan to pick up with example 4 next time. Is that okay with y'all? And let's see how many homework exercises you can do here. Problem 17.8. I think you can do number 1 and probably number 3. Well, just do 1. We'll pick up 3 next time. Okay, you probably would be able to do it. But you got plenty more from the other sections. So what we got left is that last example in 17.8, and then we've got 17.9 to go, and I don't think you have to do 17.10 or 17.11 or 17.12. Now 17.12 is pretty interesting. 17.13 is interesting, but I don't think they were called for by the course description. Let me go back and look at the front of the book and make sure I'm right on that. I wrote them down in my thing. Yeah, basic electricities, 17.3, 4, 5. You had to do Ohm's law to do any of this. 7, 8, and 9. Compound circuit. Yeah, when we finish 17.9, we will do the test. So I'll try to have that test ready for you by next Wednesday. Okay? If we'd have gotten 17.9 done tonight, I would have given it to you sooner. But I'll probably put it out when I send out the announcement about the invite to the Zoom on next Wednesday. And I hope everything keeps working. All right, any last questions? Parting shots? Everybody okay?
I have a question.
Okay, what's that?
So when we get the test, when it gives these type examples, is it going to show the circuits, or is it just going to say series circuit or parallel circuit, and then we can just draw it ourselves?
I'm afraid you're going to have to draw it yourselves. That's a very good question. And the reason I say that is because I've got to type this on Word. And Word doesn't have the capability of drawing circuits. Now let me see. I wish I could just send you yeah. In fact, even on the thing, they don't draw a circuit. They just give you resistors and tell you what kind of circuit it is, and you basically have to draw them out. So there's not that many to do. A lot of the questions here come from the earlier part of the chapter, so you don't have that many with this. In fact, the first 5 questions are from the first part of the chapter, and then the last 5 are from what we're just talking about. Well, actually, even the 10th question here, well, actually more than that. There's only a few Ohm's law questions. Maybe 3 or 4 of those are Ohm's law questions. The rest of them are the other formulas we had. So yeah, you don't have that many, and you probably could get away without drawing, but if you wanted to draw them, you certainly could. And
so does the first part of the test focus on like?
Okay, a little louder. I was too far away. Say it again.
So you're saying the first part of the test focuses on like electric force, stuff like that?
Yes, exactly. The first part of the chapter, right? Because there was a lot we talked about there, resistivity and other things like that. So that's what it focuses on. I think there's only 3 questions that are Ohm's law type question, parallel and series. I think 2 of them are like that, and 1 of them is just a regular Ohm's law question. So I don't think you have a compound circuit involved in it. I was just glanced at it. I don't remember seeing one. But that's what we'll be doing.
So it will specify series circuit and parallel circuit. It'll specify.
I believe it says. Let me get it back again. I just put it away. Let me see. Here it is.
You have to, like, when you're finding resistance, you find it in different ways depending on the circuit. So I was just wondering if it's going to specify or not.
Okay. Here we go. Let me look again. As you said, the first one's an electric force problem. The next one is an electric force problem. The next one is an electric force problem. The next one is a resistance problem, and a pretty simple one. And then one is a resistivity type problem. And the next one is just a plain old Ohm's law problem, just simple, not special. And okay, if I forget to tell you this, the question 7 refers to the circuit in question 8, okay? It just says in the circuit below, but there's no circuit given there, but it's the circuit they're talking about in question 8. And that is a series question. And then the next one is a resistance question. And then the last one is basically another force question. So you only have one, and it's a series. I don't think they have any that are parallel. I don't know why. Like I said, this is not a very good test bank. And I tried not to go outside the test bank, because if I do that, I make the questions too hard. If I think, oh, this is easy, then it never is. Okay, so yeah, you only have one, I think, series one to deal with. So it's not going to be that bad. Any other questions? Good questions, by the way. I've got a lot of typing to do to get it done, because if I were doing this in WordPerfect, that would be great, but y'all don't have WordPerfect, or maybe a few of you do. I've got to send it in Word, and that Word is not nearly as easy to use for symbols and stuff as WordPerfect. So it's going to take me a while, so I hope I'll have it ready by next Wednesday. I think I will. All right, any other questions? Good deal, good class. I'm glad y'all were all here. Good number of people here. Missing a bunch at the top of the alphabet, but from there on down, I think everybody was here. So the first 4 students at the top of the alphabet weren't here, so I don't know where they are. But I'm glad y'all saw it on your email, because I couldn't put it on Blackboard like I usually do, because my system wouldn't support Blackboard because of the hotspot wasn't strong enough. So glad y'all saw it and were able to be here. Have a good weekend. Stay safe, and don't work too hard. Well, work as hard as you need to. Okay. Take care. Any last thoughts? Parting shots? Okay, I'm going to stop the sharing and find the end of meeting, and I'll end it for everybody. Take care.